Well, good morning and welcome you to all to this session of fluid mechanics. As I told in the last class that today we will be discussing incompressible viscous flows. Now, first of all, we have to know what is incompressible viscous flow. The flow is incompressible means when the change of density is not taken into account. That's true. Now, viscous flows means that flow of viscous fluids. All fluid has viscosity. All real fluids have viscosity, and flows of all real fluids are therefore viscous flows. Now, what happens for real flows? The property viscosity is manifested in terms of generating shear stresses or the frictional forces between the fluid layers and fluid to solid surface. As a consequence of which we know that the velocity of the fluid particle adjacent to the solid surface is zero, relative velocity is zero. That means if the solid surface is at rest, the fluid velocity is also zero there at the solid surface. Now, earlier sections we have discussed the flow of inviscid fluid or inviscid flow. This is a hypothetical situation where we consider the fluid viscosity is zero, and flow of such fluids are known as inviscid flows or flows of inviscid fluids. There we have found out because of the absence of viscosity, the velocity at a cross section is uniform, and which violates the practical findings that the velocity at the surface is zero. That means there is a velocity at the surface also. So now in these classes of flow we have seen the equation of momentum, which is known as Euler's equation, contains only the pressure force as the external surface forces. Of course, the body force is there. Body force depends upon the external forces imposed on it. That is not connected with fluid mechanics, whether there is a body force field or not. In general, we consider the gravity is the only body force field if there is no external force imposed on the flow of fluid. So therefore, the surface force on a fluid element, we recognized only the pressure forces, which is normal, and we know which is same in all directions, which is known as hydrostatic or static pressures, or we call it as thermodynamic pressure. So this is the only force acting on it, and we know that the Euler's equations can be written in three coordinate directions along with the continuity equations. Now the basic philosophy is like that, if we have three equation of motions, that means in three coordinate directions x, y, z with three velocity components, you know what is Euler's equations, and then the continuity equations, then we have four equations, and at the same time we have four unknowns u, v, w and pressure, because density is constant, the flow is incompressible too. So these four unknowns and four equations we can solve for it. But we have seen in many situations we don't have to solve directly the Euler's equations to know the velocity. Why? This is because if the flow is specified by the flow rate q, we know that if you divide the flow rate by the cross-sectional area, we get the velocity, and that velocity is uniform at a cross-section. So therefore, Euler's equation is not sought for the solution of velocities. These are very important things. I am telling you, this will not be given in any book, even in not in my book also. I have not written like that. So therefore, sometimes it is not required. So why then Euler's equation is required, or the Bernoulli's equation, the integrated form of Euler's equation, to know the pressure variations. This is simply done in case of inviscid flow, we have done earlier. But in case of a viscous flow, you see again the equation of motions in three coordinate directions, we have got three equations. Along with the continuity equations, we have got four equations, and we are with four variables, three velocity components in three directions or axes, and pressure, taking density to be constant for incompressible flow. There we have to solve these equations, all these four equations, equations of motions and the continuity equations, to solve for velocity components and pressure, even if the problem is specified with a given flow rate. Why? If we know the flow rate, and if we know at any cross section the cross sectional area of the duct, if we divide the flow rate by the cross sectional area, we get a velocity which is defined as the average velocity of flow. That is flow rate divided by the cross sectional area. It's very important. But we don't know what is the velocity variation across a section, and it is the viscosity of the fluid which makes a velocity variation across a section. This probably I discussed in the very first class, that is the manifestation or the cause of viscosity is to make a velocity distribution across a section, that is a normal to the direction of flow. And ultimately the velocity at the solid surface will be zero provided the solid surface is at rest, that is the no slip condition. So to know the exact velocity variation across a surface and also the variation of velocity along the direction of flow, along with the pressure variations, we will have to solve the equations of motions. So it is not that easy that flow rate by area is the velocity and velocity is obtained, because it is not a uniform velocity across a section. So therefore the very first task that comes in learning or studying the viscous flow is to develop the equation of motion for viscous flow. The same equation of motion, that means the Newton's law applied to a fluid element. But here the difference is that if we consider a fluid element, its surface forces, that is the forces acting on its surfaces that have been taken isolation from the entire fluid body, are not consisting of only the pressure forces but the shear forces. So therefore the nature of the shear forces acting on the surfaces and their relationship with the shear strain or shear strain rate helps in developing the equation of motion in viscous flows. So first part we will be concentrating our attention to that. So in doing so, we first recollect, it is a bit of recollection because you have already done it in your applied mechanics class, the stress system of stresses in deformable body. Better you write it, system of stresses in deformable body. System of stress, rather you write, in a deformable body. This is any deformable body. Please, any question you can ask me. Deformable body. So just it is a recapitulation. Now if we consider a Cartesian coordinate system, XYZ rectangular Cartesian coordinate system, and consider a fluid element and a parallelepiped fluid element, we see that there are 6 planes, as we have already recognized that X plane, Y plane, Z planes. X planes means the planes whose perpendicular is the X direction, accordingly the Y plane whose normals are the Y directions, and Z planes whose normal are the Z directions. So you see, we define the stress like this. Already you know the stress is defined by 2 subscripts. One subscript stands for any stress, let tau, with 2 subscripts 1 and 2. One subscript stands for the plane on which it acts, another subscript stands the direction. That means on a plane there may be a different direction. Direction is compatible with the coordinate axis. So therefore to represent stress we require 2 degree of freedom. That means the stress requires 2 specification. That is why stress is not a vector, it is a tensor of order 2. Those things are known to you. So with this notation we just fix. Now when a stress acting on a plane and along the direction normal to the plane, that means this stress is on a plane and along the normal to the plane, that means along the normal to the plane means along perpendicular to that plane, then that stress is normal stress, and this is usually denoted by sigma, where the stress acting along the plane, not normal to the plane but in different directions, are known as shear stress, as you know, and denoted by sigma. So therefore when we write denoted by tau, sorry. So when we write sigma on any plane, its direction is fixed. So therefore sigma is not denoted with 2 suffixes. So therefore if we see that this is one x plane and this is another x plane which is separated by a distance, I am sorry, this I have not done, this is dx. We consider a parallelepiped of dx dy, and this one is dz. That means this one is dz, this height dz. So another x plane separated by a dx. So here the stresses are like this. This is the sigma x plus del x, sigma x dx. This will be the sigma x. I am sorry, this will be the sigma x. This is the sigma x. Similarly, you see that there are 2 stresses, tau xy and tau xz. It is the x plane along the y direction, this is the x plane along the z direction, and they are appearing in this way as a couple, that means pair. So this is the tau xz, but it has an increment for dx, del x of tau xz, del x of tau xz dx, I am sorry, del x of tau xy, I am sorry, del x of tau xy, I am sorry. So this should be del z, but this is with the del z, this is different, but this is sigma x is this one, tau xy is this one, and tau xz is this one. So this will be tau xy, so this will be tau xy, so I am sorry, this will be tau xy plus del y of tau xy dx. So this will be this, I'm sorry. So this will be tau xz and this will be by mistake del x. That means tau xz and tau xy has been increased due to a change in the distance dx. So this will be. So these 3 stresses appear like that. Similarly, if you see the stresses in the y plane, that means this y plane, this plane and this plane. If I give a name, then that will be better. A, B, C, D, well, E, F, G, H, this is simple thing. So if I consider the plane A, B, C, D and E, F, G, H, then this is sigma y, this is tau yx. First suffix is the plane and the second suffix is the direction along x axis and tau yz. Similarly, they appear like this. You see, that is sigma y, and this sigma y has changed for a distance of dy. So that means this is the plane EFGH. I have given the green color. So sigma y del y of sigma y dy. Well, and similarly this will be sigma y. I am sorry. So this will be this is not properly shown. So this will be again tau yx. That means this is the tau yx. That means this tau yx, this will be tau yx dy. Well, and this is tau yz. This is the tau yz. So this is written as, well, tau yz. Where it is written? Have I written tau yz? No, it is not written. So you can write this. This one is tau yz plus del y of tau yz dy. So that means these three stress components, normal stress and the shear stresses, they appear like this. Del y of, this is tau yz, this is tau yx, this is tau yx, and this is the sigma y, and this is the sigma y. This is an incremental change. Similarly, if you see the jet planes, please see that DC H G, DC GH, and another jet plane separated by a distance dz along the positive direction of jet, that is ABFE. And if we see the red one, that is stress system, one is sigma jet, another is tau zx, that is jet plane x direction, another is tau zy. And similarly, they are being shifted like this. They are being shifted to the plane ABFE, that is sigma jet. This is the increment del z of sigma jet del z. Similarly, tau zx, del z of tau zx dz. Similarly, this one tau zy del y of tau zy del z. This way we can represent the stresses. Now this is very simple, that if we now want to find out what is the force in the x direction, what is the total force in the x direction. Total force in the x direction, if we want to find out, we have to find out the force in the x direction. One is x direction force. Now we have to see the planes. Now for x planes, the contribution of x direction force is, that is sigma x only. That means you see, therefore sigma x, this minus this, so this ultimately will come del x sigma x into dy dz, plus x direction force will come from the y plane, contribution of y plane, that is tau yx and tau xy, that means this one. So tau xy minus tau yx plus del y of tau yx minus this one. So therefore this comes del y of tau yx dy, and the area, it is dx dz, dx dz. So therefore we see this is due to the x direction force in x plane. So this is sigma, represent the x plane. So this is the force in the y plane but x direction. Similarly, the force in the jet plane but x direction, this is tau zx. That means this one, tau zx plus del z of tau zx dz minus this. Of course, this will be multiplied with the area, that means dx dy. That means this will ultimately give rise to del z tau zx dz dx dy. It is very simple to remember that del x of sigma x plus del y, that means change with y. What is that? The x direction force but in y plane. So whenever there is a differential del z, it has to change with respect to z. That means the force will be in jet plane, but it is in the x direction. Always we are writing in the x direction. So this will comprise the net x force per unit volume. Let Fx by per unit volume, where V is the volume of the parallelepiped. So therefore we come to this, that del x of sigma x plus del y of tau x, tau yx suffix plus del z of tau zx is the x direction force per unit volume in this elemental fluid. Similarly, the y direction force per unit volume will be equal to, if you see that first x direction force, if you find out what is the x direction force from y plane, if you start the y plane x direction force come only from tau yx and tau xy, and this will be del x of tau y plane. So this is the first plane and then this is the direction. That means we are finding out x plane and y direction. Okay, we start first with the x plane, that is better. We start with the x plane and the y direction force. So x plane y direction force means it is tau xy, it is tau xy. So therefore x direction y plane, so tau xy. Okay, then del y of sigma y. Then y plane, then we come to y plane. So what are the y direction force in y plane? This is only sigma y. So this contribution will be del y sigma y. Dx dy dz is coming here. Plus we will now consider z plane. Z plane contribution for y direction force will be what? Tau zy. Tau zy. So this one, tau zy, this one, tau zy. So del z of tau zy. So we see that the force per unit volume in any direction, the directions is y. And when del x, it is tau xy. That means the force in x plane y direction. Del y, sigma y. That is the force in y direction in y plane. Del z, force in y direction and z plane. It is differentiated like that. So this is the force per unit volume in the y direction, in the z direction. If you make the force analysis, you will come to this. All okay? Now if I write the force in z direction per unit volume, please, you come with the x plane. What is the force in the z direction in the x plane? This is contributed by tau xz. This is contributed by tau xz at these two places. And if you make it multiplied with the area and subtract, then you will simply get del x of tau xz. That means at the x plane it is appearing, but it is appearing in z direction. That's why del x we are differentiating with respect to x, because it is appearing in the x plane. Similarly, after x plane, if we go to y plane and we recognize that z direction force in y plane is contributed by tau yz. Okay, so tau yz. So these are the z direction force in y, tau y. So difference between this and this, of course, multiplied with the area, and that will be giving you del y of tau yz. The first one is y, this one y. That means differentiation with respect to y when the force appearing in the y plane. And second suffix is z direction. This is consistent because it is the force in the z direction. And similarly in the z plane, the force in the z direction is this. So there is a very much good rhythm that the net x force in x direction is this, del x sigma x tau yx plus del z tau zx, all x direction force appearing in x, y, z plane. Similarly, net surface force per unit volume in y direction are all y direction force appearing in x, y and z plane. Similarly, the net z direction force per unit volume is contributed by all z direction forces appearing in x, y and z plane. So simple force analysis will give this thing. Now after this, probably I am not going to prove it. You know that you can prove the another thing. Okay, before that I just tell you that with this in mind, so we see that there are three quantities. Again let me write this. So Fx per unit volume is del x of sigma x, well, plus del y of tau yx plus del z of tau yz, tau zx. So all x direction force. Similarly, Fy per unit volume is x plane. We start with the x plane first. So y direction force, that means x plane y direction force, plus y plane y direction force means sigma y, plus z plane, that means force in z plane but y direction zy. Very simple to write. Fz by v is again x plane z direction force, that means xz, plus y plane force in z direction, that means it has to be a tau, y plane z direction, and z plane z direction, it has to be a normal stress. So therefore we there are 6, 1, 2, 3, 9. These 9 stresses which define the entire state of stress. So, entire state of stress is therefore defined by 9 stress quantity. So, I write this stress quantity x, y, sigma y, tau z y, tau x z, tau y z, and this forms a matrix where the row of the matrix represent the stresses in particular direction. These are all stresses in x direction, y direction, z direction. These are all known things. That's why I am little fast. And the columns represent the plane, that is the stresses acting in x plane, y plane and z plane. So ultimately these 9 stresses, this is known as stress matrix or stress tensor. Matrix, this is the elements arranged in an array known as matrix, and tensor means the quantity which requires, apart from its magnitude, more than one specification. Vector requires one specification more than its magnitude, but tensor requires more specifications, more than one specification apart from its magnitude. It requires 2 specifications. Actually it is tau xx, tau yy, tau zz, but we are writing is sigma, that's why 2 suffixes we are omitting. So that's why it is tensor of order 2. This thing probably you know. Now you also know from the rotational equilibrium of the element, that is the parallelepiped, if you consider the rotational equilibrium of parallelepiped about any of the axes, that means about y or x or z, we can see, we can show that this is equal to this, the symmetrical element about the diagonal. These are the diagonal element, and tau zy is tau yz. That means tau yx is tau xy. This probably you know, I am not going to prove it. Tau zy is tau yz, and tau xz is tau zx. This can be proved if you consider its rotational equilibrium. If you write its rotational equilibrium equation, that means torque is equal to I into omega dot, where omega is the angular velocity, omega dot is the angular acceleration about any axis. Let us first consider about y axis. Then the shear stresses will appear on z planes and on y plane, x planes. So this will cause the rotational motion of the element about the y axis, and if I write it and considering dx, dy and dz to be very small, take the limit, you will be able to prove that. This I left you as an exercise, probably you have done it earlier. So if you take this, that means this is equal to this is equal to this, and this is equal to this. That means there are 6 unknown stress quantities which define the stress system. So therefore 6 unknown quantities are there. Now we write that therefore if I come to the equation of motion for this fluid element, rather I again draw this element like this. I again draw this element like this. Well, I again draw the element like this. Okay. So let this is x direction, this is y direction, this is z direction. So this is dx, well, so this is dy, well, and this is dz. Then I know that the force per unit volume Fx by V for this element is this, force per unit volume in the y direction, force per unit volume in the z direction. Now what is the total force acting in x direction? Let us now consider the Fb is the body force per unit mass, body force vector per unit mass, which can be represented as Fbx I plus Fby j plus Fbz k. That means this has got 3 distinct components in x, y, z coordinate. Therefore, total force per unit volume in x direction will be what? Total force per unit mass, per unit volume in x direction. What is total force per unit volume in x direction? You tell me. Total force per unit volume in x direction F. So I am already using F. So better you write total force in per unit volume in x direction is equal to del x sigma x plus del y tau sigma x del del y yx, but now it is not very essential xy or yx del del z in z plane but x direction, but xz and zx are same, plus rho into fbx. If I define fbx as the x component of body force per unit mass, rho is the density, total force per unit volume in x direction, and that must be equal to its mass into acceleration per unit volume. That means the inertia force, negative of the inertia force per unit volume. That means mass into acceleration per unit volume. So what is its mass? Rho dx dy dz. What is the acceleration? Du dt. So per unit volume dx dy dz. So this dx dy dz cancels out. So this becomes is equal to rho du dt. Alright, or one can write the rate of change of momentum, one can write d dt of momentum. What is the momentum? Mass rho dx dy dz into u. But rho dx dy dz being the mass of a system which by definition is fixed, it comes out. So it becomes rho du dt. And this dx dy dz, it cancels from left hand and right hand side. If we equate this with this, then this has to be written as total force. So either you write the rate of change of momentum with the total force, or you write total force per unit volume in one direction with the mass into acceleration divided by volume in that direction, which ultimately makes you rho du dt. Or you write total force in the x direction, that means multiply this with dx dy dz and multiply this with dx dy dz. That means the entire right hand side is multiplied with dx dy dz is equal to rate of change of momentum in x direction according to Newton's law. So there, remember it. Sometimes even in the Viva Voce board we ask that why rho comes out. Is it for incompressible flow only? No, it is for compressible flow. There is no restriction for incompressible flows. So rho comes out. This is because in the deduction we see that rho dx dy dz as a whole mass of the system comes out. So that dx dy dz get cancelled. So rho du dt is del del x of sigma x del del y. And this way I can write the equation of motion in y and z directions accordingly. And this comes out to be like that. In x direction I write rho du dt is equal to, I write the body force term first, the convention, plus the surface force sigma x plus del del y tau yx or tau xy immaterial, but still I follow the notation zx. Similarly, this is the mass times acceleration per unit volume equates to the net force acting in y direction per unit volume, that is del del x of tau xy. These two are equal, tau xy or yx, del del y of sigma y plus del del z of tau, that is the y plane zy. Well, and rho dw dt is fbz plus z direction. Rho dw, rho is missing, oh very good, plus del del x of tau xz plus del del y of tau yz, sorry, plus del del z of sigma z, because fbx, fby are the body force components per unit mass. So these three constitutes the equation of motion of a deformable body or a fluid body in x, y, z directions. But here you see the left hand side is the velocity. It can be expressed in velocity component. This is the substantial derivative which can be split in terms of its local and convective. But the forces are expressed in stress form. Now this part is beyond, it is not within the jurisdiction of fluid mechanics. It depends upon the physics of the body force field. Usually body force field is a gravity force field whose physics is very simple, and we can find out what are the components depending upon the choice of the coordinate axis. But the main task of deducing the Navier-Stokes equation, because our main objective, you must know, to develop the equation of motions, for example in three coordinate directions x, y, z, in terms of the velocity components. Here velocity vector v is defined as that u v, that means already you have recognized it, that u, v, w are the x, y, z component of velocities. That is, this is the x, this is the y, this is the z rectangular coordinate axis. That means our main objective will be to develop x coordinate, x direction equation of motion, y direction equation of motion, z direction equation of motion in terms of u, v, w, and it may include pressure P. It may include viscosity, coefficient of viscosity mu, which we have read at the very beginning in our course. So how to do it? So the next task is to relate these stresses in terms of the strain rates, so that the relationship between stress and strain rates will ultimately induce these variables to come in this equation, and that is the most important and pivotal point of deducing the Navier-Stokes equations. So relationship between stress and, I have told you earlier, the difference between a fluid and a solid is that strain rates. So it is not the strain, but it is the strain rates. So this is the most vital part, relationship between stress and strain rates components. So how to do it? This is beyond the scope of your discussion, your study or your syllabus. This is usually done at the advanced level of fluid mechanics class. So relationship between stress and strain rates component. Without going for this deduction of this relationship between stress and strain rates component, I will tell you, which are very important to know, how the relationships are deduced, final relationships, and what are the assumptions. So this is one of the toughest job, and it requires a higher algebra to develop this relationship between stress and strain rate components for in general for a fluid. But if we take few assumptions, this becomes little easier. So what are the assumptions that are made? First assumption is that this relationship is linear. Why this assumption is made? It is Newton first who found out that there are different number of fluids or class of fluids which obeys a linear relationship between stress and strain rates. These fluids are known as, according to his name, Newtonian fluid. So therefore the equation of motions which will be developed for viscous flow, this is for Newtonian fluid. That means this is a viscous fluid, but Newtonian fluid. If I ask you what is Newtonian fluid, where the relationship between stress and strain rates are linear. Another thing is that this relationship is invariant with coordinate transformation, That means either a rotation, both, or translation. If you give a translation or rotation of the coordinate system, this relationship is invariant with the coordinate transformation. What does it mean physically? If a relationship is invariant with coordinate transformation, what does it mean physically? Any intelligent student of the class? If a relationship of certain variables is independent of the coordinate transformation, what does it mean? This is a identity. This is a physical law. Identity is another name of an equation. There is a difference between equation and identity, very subtle difference. It is a physical law. Any equation defining a physical law is invariant with the coordinate transformation. Okay. Number 3 is that obeys Stokes' law. Of course, this it is very difficult for you to understand. Stokes' law. Stokes' law means second coefficient of viscosity is 0. Second coefficient of viscosity is 0. That I will describe. Second coefficient of viscosity. The fluids which obey this is known as Stokesian fluid. Usually liquids, perfect gases obey Stokesian fluid. This is now just for your information, not beyond this. The concept of second coefficient of viscosity arises when there is an exchange of momentum of energy between different degrees of freedom, like translation to rotation, rotation to vibration. So this second coefficient of viscosity arises in those cases, which is so small can be taken to be 0 for a class of fluid which is known as Stokesian fluid. So therefore, the equation of motion for a viscous fluid will be generated for Newtonian fluid and Stokesian fluid. Relationship is invariant with coordinate, and last assumption is that continuity to hydrostatics. That means the relationship should be such, the equation should be such that if we put hydrostatic condition, the continuity to hydrostatic condition, that means if you make all velocity component u, v, w 0, then these sets of equation should reduce to the equation of hydrostatics. Okay? So with all these assumptions, we develop the relationships. That means stress sigma x, okay, then sigma y, I write first the normal stresses, then the shear stress. There are 6 quantities. Now we have recognized out of 9 there are 3 x, y, y, x same, x, z, z, x, y, z. So these as function of, in general, what are the strain rates? Linear strain rates and angular strain rates. This is the linear strain rate, this is the angular strain rate. So each stress component should be in general a function of 1, 2, 3, 4, 5, 6 strain rate component. So this way 1, 2, 3, 4, 5, 6. So 6 equations with 1, 2, 3, 4, 5, 6 terms, plus additionally one constant term if we consider a linear relationship. So this will induce 42 unknowns. Because for example, if sigma x is related as a1 plus b1 epsilon x, you will be astonished to see that how it does. Epsilon z in 3 dimension plus b4 epsilon x. Now you see, sorry, I am sorry, a1, b1, c1 then. Oh, sorry, a1, b1, then you write c1, all, then you write d1, then you write e1, then you write f1, then you write g1. All looks good. So you see, if we consider a linear relationship, so general linear relationship will be normal stress is a function, linear function of all these strain rates, a1 plus b1 epsilon x dot plus c1 epsilon y dot plus d1 epsilon z dot plus e1 epsilon gamma dot xy plus f1 gamma dot xz plus, that means 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 42 unknowns. You will be astonished that these 42 unknowns will be reduced by the assumption, these 3 assumptions. This is taken care of if we express 6 equations like that, ultimately into 2 unknown. One is p, another is mu. That is beyond the scope of this class. And finally, this relationship is like this: sigma x minus p plus 2 mu 2/3 mu into del u del x. If you have any query, you please ask me. Otherwise, if you just talk in the class, I will take it very serious. Without any query, if you talk, if you have any query, you ask me. Sir, you are fast. Okay. So this I am writing as divergence of the same thing. Please ask me. Sir, what is this? We do not understand. This deduction is ultimately out of the scope of this, and tau xy is mu del u del y plus del v del x. Tau xz is mu del w del x plus del u del z. Tau yz is equal to mu del v del z plus del w del y, where mu is the coefficient of viscosity, p is the thermodynamic or static pressure. So therefore, the sigma x, sigma y, sigma z, the normal stresses and the shear stresses are derived, are developed in terms of the velocity components like that. Here you see, this is the thermodynamic pressures. So when the fluid is at rest or there is a frictionless fluid flows, the pressure, the normal stresses are only minus P. That means compressive stress, which is equal to the thermodynamic pressure. But this part is added when the fluid flows. So this part, second and third, is known as deviatoric stress. Deviatoric stress. That means stress deviates from that of the thermodynamic pressure. That is the deviatoric stress because of the friction. So this part comes because of the friction. For incompressible flow, of course, this part will become 0. Now if we add the three equations, first three, you will see that even if the flow is not incompressible, this becomes is equal to minus 3p. Why? Because this becomes 2 mu common del u del x del v del y del w del z minus, if you add these three, it will be also minus 2 mu into del u del x. So this cancels, which means that thermodynamic pressure is minus of the arithmetic average of the three normal stresses in a flow of a frictional viscous Stokesian fluid. So fluid which obeys Stokes law, second coefficient of viscosity is 0. So thermodynamic pressure is the arithmetic average of sigma x, sigma y, sigma z. Now our next task is to substitute this into the Navier-Stokes equations. So that means in sigma x, tau y x, tau z x, tau x y, sigma y, tau z y, tau x z, tau y z, all places we just substitute this and finally solve it for the velocity, that the equation of motions in x, y, z coordinate directions. So today up to this. Thank you. We are lagging behind. I am telling this takes time and